Hello, math students. Today we're going to be going over returning a polygon to its original position, going over the tutorial and the mastery test here. So please follow along, do everything I do, and it'll make a lot of sense. So let's just go ahead and get started with the very first section where you kind of have to answer some questions. Now, a lot of this lesson has to do with rotations. So if you understood rotations back in the previous lessons about transformations, then this lesson should be relatively easy. And honestly, I feel like this one's easier than the last couple for sure. Let's go ahead and get started here with question 1. And we're going to be using GeoGebra a lot, so hopefully you're relatively familiar with that and been working with that in the previous lessons. A rotation is a transformation that can map a figure back onto itself. Use the GeoGebra geometry tool to explore this property of rotations. So let's go ahead and click on this link here. Should open a GeoGebra page. Now, hopefully you know what kind of shape this is. This is a pentagon. It's a pentagon. Pentagons have 5 sides. And this is also what's known as a regular pentagon. So a regular shape is a shape where all the angles and side lengths are congruent. So you can see the length of AB is the same as the length of BC and the length of CD. They're all the same length, right? And all the interior angles there are all congruent as well. All the angles have the same measure. So let's go ahead and you should see this slider here, alpha, and when you slide it, it rotates. You see that? So we want to figure out how many degrees of rotation it takes to make this pentagon line up on top of itself. So let's go ahead and move this slider until the pentagon lines up with itself. Okay, so there's the first one, right? You see how I lined it up perfectly there? Notice how many degrees alpha is, 72 degrees. So a 72 degree rotation, the pentagon lines up on top of itself. So that's the first one we're going to put, 72 degrees. Okay, now where does C prime end up? Well, C prime ended up in the same position as where B is, right? So we're going to put a B right here. Now let's figure out the next alpha. So how many, let's go ahead and rotate it again. And there. Okay, so 144 degrees. And now C prime is where A is. 144 degrees. And that's where A is. Okay, so go ahead and continue that and fill out the rest of this. You should have 5 different angle measures there. Now, let's go ahead and move on to this one. So how many values of alpha did we have? So there should be 5. Does pentagon A prime, B prime, C prime, D prime, E prime coincide with pentagon ABCDE? What is significance about this number? Okay, so here we kind of saw that there are 5 different angles where the pentagon lined up on top of itself. So there are 5 different angles of alpha that will make the pentagon rotate onto itself. Now, what's interesting about that is a pentagon has 5 sides, 5 angles, and 5 different degrees of rotation to line onto itself. So that's the key thing here. For example, if it was a 6-sided shape, a 6-sided regular shape, a hexagon, there'd be 6 angles where it would line on top of itself. If it was a 3-sided shape, a equilateral triangle, there'd be 3 angles where it would line on top of itself. So however many sides and angles it has, that's also how many rotations there will be to line on top of itself, as long as it's a regular shape, meaning all the sides and angles are the same. Okay. Now move the center of rotation R to a different position on the coordinate plane. Next, move the slider bar to rotate pentagon ABCDE. How many times does the pentagon line to top of itself in this situation? So we're going to go ahead and go to the pointer tool, and we're going to move the center of rotation. Let's say we're going to move R over here, and let's put alpha back where it started. Okay, so now how many degrees rotation will it line on top of itself? Okay, it's not on top of itself anywhere except 360 degrees. So notice when I move the center of rotation outside of the pentagon, or anywhere really, I can move it here as long as it's not in the direct middle of the pentagon, there will actually only be one rotation where it's perfectly on top of itself, and that'll be a 360-degree rotation. So the moral of the story is this: if you rotate a shape, any shape, 360 degrees, it'll always line on top of itself. Okay, so any shape rotated around any center, so I can move the center of rotation anywhere. Any shape rotated around any center, rotated 360 degrees, will always line on top of itself. Okay, so that's what I want you to say here, that when we move the center of rotation, that there was only one angle where it lined on top of itself, and that angle was 360 degrees rotation. Okay, and it doesn't matter where you move R in that case. Okay, question 4. Move the center rotation back to the origin, 0, 0 on the coordinate plane. So we're going to move the center rotation back to there. Okay, great. Now, after Pentagon ABCDE, by moving one or more line segments on the Pentagon to a different location, rotate the Pentagon using the slider. How many times does the Pentagon map back onto itself in this situation? So let's see. It says we can move. Okay, so we can move one of the segments here. So now it's not a regular pentagon, is it? Because now I've changed it, so not all the sides are the same length. Okay, and you could change it in some other way as well. Now, let's go ahead and see how many times the pentagon will rotate onto itself. Well, only once. And once again, it's at 360 degrees. So it doesn't have to be a regular shape in order to rotate onto itself. But if it's not regular, then you're only guaranteed to get the 360-degree rotation. So let's go. And so you could describe that there, that since it's not a regular shape, it'll still rotate onto itself, but only at a 360-degree rotation. Okay. But if it's a regular shape, like a regular pentagon, like what we started with, it'll have multiple angles of rotation to map onto itself. Okay, list at least 3 shapes other than pentagons in the table. If the shape is a polygon, indicate whether the shape is a regular or irregular. Find the number of times that the shape will map back onto itself as the shape rotates 360 degrees about its center. Also note how many degrees the shape has rotated each time it maps back onto itself. Use GeoGebra to guide you in this exercise if you wish. Okay, so we're going to actually go with a 3-sided shape. So we're going to use a regular triangle, also known as an equilateral triangle. Equilateral triangle. I think I spelled that wrong, but that's okay. Also, we're going to go with a square, which is essentially a regular quadrilateral, is a square, right? Because all the sides and angles are the same. And then we're going to use a hexagon. Okay, so how many times will it map onto itself? Well, an equilateral triangle has 3 sides, 3 angles, so there will be 3 angles of rotation to map onto itself. What about a square? A square has 4 sides, 4 congruent angles, so it maps onto itself 4 different times. And for the hexagon, 6 sides, so what do you think it's going to be? Yep, 6 times it can map onto itself. For the degrees of rotation, now for this, let's think about this for a moment. So let's go back up to the very first question. The first angle of rotation was 72 degrees, okay? Now, is there a way to get that measurement without, using GeoGebra or anything like that? Well, actually there is. So I'm going to use my calculator here. And if I take 360 and I divide it by 5, which for this problem was a 5-sided shape, I get 72. So your first angle rotation, you just take 360 divided by the number of sides that you have to get the first angle of rotation there. Then once you have that 72, 72 times 2 to get the next one, right? 144. 72 times 3 will give you the next one. So the next one should be 216. I hope you got that. And then 72 times 4, and then 72 times 5, the last one should be 360. Okay, so that kind of helps us with this one as well. So the degrees of rotation for the equilateral triangle, well, triangle has 3 sides, so 360 divided by 3 gives me a 120-degree angle, will be the first angle of rotation that'll map it onto itself. Then I can do 120 times 2, so that's 240. And then 120 times 3, 360. The last one should always be 360. So these are the different degrees of rotation to map an equilateral triangle onto itself. What about for a square? All right, so we take, there should be 4 angles here in this one. So we take the 360 divided by 4 to give us 90. That's the first angle of rotation where it'll map onto itself. Then 90 times 2, 180. 90 times 3, 270. And then 90 times 4, of course, is 360. Okay, so I want you to go ahead and figure out the hexagon. So here you should have 6 angles of rotation, 360 times 360 divided by 6 to get the first one. Okay, now once you're finished with that, we can go ahead and move on. Okay, this is just kind of talking about what we said here. Now this is talking about a rectangle. In this case, a rectangle is not a regular quadrilateral. It's not a regular polygon because not all the sides are the same length, but there still has that 180-degree rotation. So some shapes, even though they're not regular, they might still have multiple angles of rotation that map onto themselves. Just depends on the shape. But like this quadrilateral, this trapezoid, it only has a 360-degree rotation. So that's it for a trapezoid. Okay. A regular hexagon rotates counterclockwise about its center. So I'm on page 10 here. It turns through angles greater than 0 and less than or equal to 360. How many different angles will the hexagon map onto itself? Well, it says it's a regular hexagon. So hexagon is 6 sides. So we've already kind of done this before. It'll have 6 times where it rotates onto itself. So 6 angles where it'll rotate onto itself. And the first angle will be a 60-degree angle because 360 divided by 6 is 60. Okay. An n-sided polygon, so n just means some general number, rotates 360 degrees about its center P. The image coincides with its preimage n times during the rotation. What can you conclude about this polygon? So we can conclude that it is a regular polygon. So this works for regular polygons. However many sides and angles it has, that's how many times it'll rotate onto itself. So a 20-sided polygon, 20-sided regular polygon will map onto itself 20 times. Okay. Let's talk about how you can map something onto itself using reflections. Okay, so we talked about rotations. Now let's go ahead and talk about reflections. And lots of shapes can reflect onto themselves. And we're going to talk about that specifically here. So question 1. All right, so actually go ahead and open this reflections GeoGebra. So this should open another GeoGebra tab for reflections. And it should look something like this with a couple of hexagons and then line HG there. All right, hexagon, this one is a reflected image of the other hexagon. Okay, so we can see that here. So this one on the left is the reflection of the one on the right. Okay, so the one on the left is the image, the one on the right is the original, the pre-image. Okay, the midpoints of the sides of hexagon ABCDEF are also shown. Okay, drag the line of reflection GH until the image coincides with the pre-image. At this location, if the pre-image flips about the line of reflection, it will flip onto itself. In how many different positions can you place it GH so that the image reflects onto the pre-image in this manner? Describe the different positions. Be sure to pass the line of reflection through both vertices and midpoints before answering. Okay, so let's go ahead and move GH. So as we move GH, it moves our image, doesn't it? Because as you change the line of reflection, that changes the image. So what we want here is to draw what's known as a line of symmetry. So a line of symmetry is where we're going to put GH. Basically, a line of symmetry is a line of reflection that would reflect the preimage directly onto itself. So let me show you what I mean here. So if I put G right here and H right here, okay, notice that this is known as a line of symmetry because the preimage and the image are completely lined up there. So you can draw one line of symmetry just like that, okay? But is that the only line of symmetry? Well, no. So that's just one. I could also move it so that I could put it right here, G on top of B, H on top of E. That creates another line of symmetry. So that's two so far. I could put another one here and here. That's three. Here and here. That's four. Here and here. That's five. Here and here. Whoop. That's six. Okay, so six so far. Should I count this one again? Well, no, I already counted that one, right? So now I'm kind of repeating. So 6 lines of symmetry. Notice a regular hexagon, a regular 6-sided shape, will have 6 lines of symmetry. So 6 lines that will reflect the image directly on top of the preimage. So in this case, describe the different positions. So how many different positions? So we want to say that there were 6 possible positions for line GF where it would be a line of symmetry. So I want you to state that there. And then describe the different positions. So how did we place line GF? Well, we placed it through the sides, but we also placed it sometimes through the vertices, right? So one side through its opposite, or one vertice through its opposite, right? So you could see, for example, where it's at right now, it's through one side and the opposite side, or you could put it on a vertex and the opposite vertex to create another one. So a vertex and its opposite, or the side and its opposite, okay? You've seen how a polygon can reflect onto itself during a transformation. Use what you know about symmetry to describe the line of reflection required for such a transformation. Be sure to use the word symmetry in your answer. Okay. So basically, I want you to state that if the reflection maps perfectly onto itself, then that line of reflection is known as a line of symmetry. Okay. All right. So now we're going to talk about different shapes here. So once again, we're going to try to use some of the same shapes we used before. We're actually going to use a equilateral triangle. We're going to use a square. And we're going to use a pentagon, so a 5-sided shape. Now, how many lines of reflection do you think an equilateral triangle will have? Well, 3. In this case, you would say the description, perhaps we could say, and if we kind of showed it, it would be like through one vertex through the opposite side. Through each vertex and the opposite side. Hopefully you can kind of envision that, right? Like if I have an equilateral triangle that, try to draw an equilateral here, that it would have 3 lines of reflection, and they would kind of go up like this, one like this, one like this. Okay, so that would have 3 lines of symmetry there. Now, what do you think for a square? How many lines of symmetry or lines of reflection would a square have? What do you think? Well, 4, right? Because it would have, and then in this case, you'd have the 2 diagonals, and then you would have the connecting sides. So two diagonals and lines going from one side to its opposite. I can put 2 here. So 2 diagonals and then 2 lines going from one side to its opposite, right? Hopefully you can imagine that. Pentagon, how many lines of reflection? A regular pentagon is going to have, we should say that this is going to be a regular pentagon. We'll have 5 sides, 5 angles, and 5 lines of symmetry. And also from the previous section, 5 rotations onto itself. Okay, so how would we describe this? You could say just like how you did here. So through each vertex and the opposite side. Okay, generally odd numbered shapes will be the same there. Question 4, review your work for questions 1 through 3. What pattern do you observe regarding the number of lines of symmetry through a regular polygon that will map the polygon onto itself? How does this number relate to the number of lines of symmetry for the same polygon? Okay, so basically you should say basically what we've been discussing. However many sides the regular polygon has also determines how many lines of symmetry we can expect to see. Some regular polygons have an even number of sides. Other regular polygons have an odd number of sides. How does the number of sides, even or odd, affect the position of the reflection for mapping the polygon onto itself? Explain. Use GeoGebra to guide you if you wish. Okay, so this is kind of a complicated problem, but we've actually kind of discussed it a little bit. Remember, if it hasn't, let's go back up to number 3 here. Both the triangle and the pentagon had odd number of sides, right? Triangle 3 and the pentagon 5. Those are both odd numbers. So in both of those cases, the lines of symmetry go from the vertex to the opposite side. Whereas if it has an even number of sides, say a square or a hexagon, 4 or 6 sides or 8 sides or any even number of sides, then it goes for diagonals, so vertex to the opposite vertex, as well as sides to the opposite sides. Okay, so it's a little bit tricky, but hopefully you might have to rewatch that again to get the full to understand it fully. But basically, if it has an odd number of sides, then it'll have lines of symmetry that go from vertex to opposite side. And then if it has an even number of sides, then you'll have diagonals. In other words, vertex to the opposite vertex, and then sides to the opposite sides. Okay. Let's go ahead and move along. Okay. All right, so let's determine how many lines of symmetry each of these shapes have. Well, one thing, I'm looking at the square, right? A square is a regular quadrilateral. So 4 angles and 4 sides, all the same, 4 congruent angles, 4 congruent sides. So it'll have 4 lines of symmetry, or in other words, 4 lines of reflection. The regular pentagon is going to have 5. Easy peasy. Okay. Now, what about the rectangle here? Well, the rectangle has 2 lines of symmetry, one going like this and one going like this. The diagonals actually won't work here. And the reason why, it's not a regular shape, right? Like a square is a regular shape. So this one has 2 lines of symmetry. And lastly, this trapezoid doesn't have any lines of symmetry at all. There's nowhere you can reflect it onto itself. Okay, so now let's go ahead and move on to the mastery test. And let's go ahead and get started here. Get started with question 1 here. Okay. Now I'm gonna, by the way, if you're not subscribed already, please subscribe. I know most of you guys aren't, but it really helps me out if you guys subscribe. Also, like and share a comment. And if you have any questions, comment them as well. Question 1. By the way, you're going to have 5 of these questions. I have 10 questions here, but you're going to be given 5 of these. So you may need to scroll along and find your specific questions. So I don't know which ones you'll have. The square rotated about its center by 360 degrees maps onto itself how many times? So it's a square, four-sided shape. How many times will it rotate onto itself? You can reflect the square onto itself. How many lines of reflection will it have? So again, a four-sided shape will have how many rotations onto itself, and as well as how many lines of reflection. So if you're paying attention to the tutorial, this should be an easy one. Select the correct answer from the drop-down menu. So here we have a octagon, that's 8 sides. The minimum degrees of rotation by which the octagon will map onto itself is, so this is the lowest number of degrees to map onto itself. So in order to do that, you take the 360, because the 360 is always the full rotation, and divide by the number of sides. Okay, whatever that is, that'll tell you the angle, the first angle that rotates onto itself. It will take blank increments of that degree clockwise rotation for A prime, the image of A, to coincide with C. So going clockwise, going from A to C, you're going to have to do 2 rotations there. Going clockwise. Okay. All right, let's take a look at this one. This is a decagon, that's 10 sides. So we have 10 angles, 10 sides, and it's regular, meaning all the sides and angles are congruent. Okay, we're going to rotate it clockwise about its center from the polygon. Okay, match each angle of rotation to the point A prime. Okay, so the first angle of rotation, we take the 360 divided by 10. So the first angle of rotation that'll map onto itself is a 36-degree angle. So a 36-degree angle will move A to B, all right? Well, to move it to C, we would do that 36 times 2. So it'll be a 72-degree angle to get to C. Then 36 times 3 to get to D. So in order to get to D, it was a 36 times 3, that's 108 degrees. Okay, so each increment around, so from A to B was 36, then from A to C, it's 36 times 2, right? So each rotation is 36 more degrees. So figure out how many degrees to get to F, H, and I, going clockwise. Okay, next one. A regular octagon rotates 360 degrees about its center. How many times does the image of the octagon coincide with the preimage during the rotation? So we're going to take an octagon, that's 8 sides. How many rotations can it rotate onto itself? So if you're paying attention to the lesson, the tutorial, then this should be an easy one. Octagon is 8 sides. Okay, which transformation will always map a parallelogram onto itself? So a parallelogram will always rotate onto itself 180 degrees. Okay, and also 360. Fiona is drawing polygons on a computer. She wants to map a regular 9-sided polygon back onto itself using a reflection. Which set of lines can Fiona choose from her line of reflection? Any line passing through the center of the polygon? No. Any perpendicular bisector of one of the sides? I think that works. Any line joining, or no, actually it doesn't. Any line, actually I think it does. Any line joining the midpoints of 2 sides? No. Any line parallel to a side of the polygon? No, it's going to be this case. Okay, that's a little bit tricky the way it's worded, but that's it. If a 12-sided regular polygon rotates about its center, at which angle of rotation will the image of the polygon coincide with the preimage? So you could take the 360 and divide by the number of sides. That'll tell you the angle of rotation that'll map onto itself, at least the first angle of rotation. An irregular parallelogram rotates 360 degrees about the midpoint of its diagonal. How many times does the image of the parallelogram coincide with the preimage during the rotation? For parallelograms, that's going to be twice, unless it's a regular parallelogram, like a square. But this one's irregular, so it'll rotate just twice onto itself. Okay, this one's kind of tricky. A regular pentagon shares a common center with a regular hexagon. If segment LM is parallel to segment AB, okay, LM and AB are parallel. Across how many lines of reflection can the combined finger be reflected to map onto itself? So this is a tricky one, but let me go ahead and grab this image and let's go ahead and see how many lines of symmetry or lines of reflection we can make here. So this one is a line of reflection for both those shapes, isn't it? So we know this one works. Would any others work? So perhaps this one. Does that work? Not sure. Probably not, right? Maybe like that. So I'm not sure. I know it's at least one. I'm going to go with probably. So here I want to connect from here to there. I want to say that it's just one. I want to say these are not true ones. I'm going to look at the answer key here. Okay, in this case, yeah, just one. So just be the vertical one. That was a tricky one. Okay, last one. So let's go ahead and take a look. This one's kind of similar where we have a shape in another shape. So we have a square inside a hexagon. Okay, so we have a square, they share a common center, and that AB is parallel to GH, so GH and AB are parallel. The combined finger rotates clockwise about its center, at which angles of rotation will the image coincide with the preimage. So for this one, let's go ahead and write down all the ways that the hexagon, so first looking at the hexagon, how many degrees of rotation does it map onto itself? Well, you take the 360 divided by 6 sides, so it's a 60-degree angle, then multiply that by 2, so 120, then 60 times 3 is 180, then 60 times 4 is 240, then 60 times 3 is 300, and then of course 360. So these are all the angles of rotation to map the hexagon onto itself. Now, what about the square? Well, if you take the 360, it's always 360 because that's a full rotation, divided by 4 sides, that gives us our first angle of 90 degrees. Then 90 times 2 is 180. Then 90 times 3 is 270. Then 90 times 4, of course, is 360. Okay, the last one should always be 360. So how many do they actually share? Well, they share the 180 and they share the 360. So there's actually only 2 times where this shape will map perfectly onto itself. So 180 and 360, so the 180 in this case. Okay, so that's it for this one. If you found this video useful, please like, comment, and subscribe. I know most of you guys are not subscribed, so if you could, please do that. It really helps me out. If you have any questions, comment them below, and I'll see you guys next time. Take care.